All right, so we're going to pick up where we left off last time. I had introduced you to Markov chains, and we had then started looking at what I consider the sort of intuitive picture of Markov chains, which is thinking about them as random walks on graphs. And we used the graph model to understand some of the key technical requirements for a Markov chain to be well behaved, right? We sort of wanted strong connectivity, and we wanted aperiodicity, right? But subject to these sorts of technical conditions, we had this fundamental theorem which tells us there was this unique stationary distribution pi, which when you are in that stationary distribution and you take a step of the Markov chain, your distribution doesn't change at all. You remain in the same state, the same distribution over states. And this, of course, was very powerful because once you know that the distribution is unique, as soon as you exhibit some distribution that is stationary, then you know that is the stationary distribution, and you don't have to worry about any other possibilities. And that stationary distribution had some nice properties, right? In particular, the time it takes to return to a particular state in expectation was just 1 over the probability of being in that state. Right? And then we used some of this machinery in order to understand random walks on graphs. Right? And we started by thinking about the vertex Markov chain, where you go from vertex and from each vertex, you just pick a random neighbor to get you to the next vertex. And then we detoured to thinking about the edge Markov chain. Right? And the edge Markov chain was very nice because it had a uniform stationary distribution. And that told us that the return time to an edge was equal to 2m, right? The expected time to return to an edge was 2m. And from that, we were able to conclude things about the original random walk on the vertices of the Markov chain, right? We showed that the cover time of the vertex Markov chain was order of mn, right? By considering the time to traverse a spanning tree. And I'm going to put traverse in quotes because we don't necessarily cross those edges in an actual DFS, but that's the spanning tree sort of guides us about where we are in the graph. Okay. And so that was most of what we did last time. And then right at the end, I started talking about reachability in limited space. Okay, and this question of, given a graph G, can you reach T from S, right? And in our standard model of computation, this is a very straightforward question, which we answer using depth-first search or any other kind of graph exploration algorithm. But how little space can you use? Okay. Because the sort of algorithmicists and complexity theorists are interested in optimizing all sorts of quantities. We usually talk about optimizing time, but it is also interesting to ask about optimizing memory. And in this model, we are generally talking about sublinear space. That means that we assume that the input is available, but read only. And so we don't count the size of the input as part of the measure of the space that we're using, but instead we keep track of the amount of extra space where we write things down in order to execute the algorithm. Okay. And what I observed last time, or sorry, what I mentioned last time was that there was this classical deterministic order log squared n time space algorithm, which basically used powering the adjacency matrix. Log n times, right? We talked about this in terms of computing shortest paths, that if you take the nth power of the adjacency matrix, this can tell you which vertices can be reached from which other vertices. And if you think about it, as long as you're willing to keep on recomputing the intermediate values as you need them, you can really think of powering this adjacency matrix as something that can be done with sort of log n layers of recursion. That is, the nth power depends on the n over 2 power recursively. And so in order to construct the nth power in a small amount of space, you recursively construct the n over 2 power in a small amount of space, and then look at its entries in order to get the nth power. So that was where things stood for a long time, but then randomized, there was this observation that at least for undirected graphs, you can do better. Okay, and it's based on this idea that the expected time to cover, to reach t from S is at most the expected time to cover the whole graph. Order mn. So if you run for mn time steps, or sorry, the expected time to get from S to T is at most mn. So if you run for twice this, then the probability that we don't reach T is at most 1/2, right? And now if we just repeat this log n times, or order log n times, then the probability that we don't reach T is 1 over a polynomial, because we multiply all those halves, right? And so this gives us a randomized algorithm that succeeds with high probability if you can reach S from T. The space needed, right, was you have to remember the current vertex that your walk is on, and also the current time, so that you know when to give up, right? And each of these takes only order log n space to write down the integer, which represents either the identity of a vertex or the time. So this gives us an order log n space randomized algorithm for testing reachability. And that's where I left off last time. So are there any questions before I dive into the new? No? Okay. So a few interesting questions remain around this algorithm. First of all, why am I talking only about undirected graphs? Well, the answer is that directed graphs can be much worse. Okay. I can give you a directed graph which looks like this. I'm going to draw a directed line. Okay. But I'm also now going to create, if any of you remembers playing Chutes and Ladders when you were a kid, I'm creating these slides that go all the way back to the beginning from every vertex. Now, who wants to tell me what's going to be necessary in order for me to cover the graph, which equivalently just means get from the leftmost vertex to the rightmost vertex in a random walk?
You have to basically get like n coin tosses, right?
Exactly, right? So you notice that each vertex has two edges leaving, and every time I take a wrong edge, I go back to the beginning and start over. So in order to get to the end, I have to take the right edge on every single step, and I only have a 50-50 chance of doing so. So the probability that I get to the end before I return to the start is just 2 to the minus n, right? And so it's going to take me 2 to the n trials in order to get to the end. And that means that it's going to take, the expected length of a trial is constant because I usually go back to the beginning right away. So the expected time to reach the end is actually 2 to the n as well. Okay. So random walks do not work well on directed graphs. But they do work great on undirected graphs. Okay. All right. So now that we have this randomized small space algorithm, what is the obvious next question?
Can we de-randomize?
Yeah. Can we de-randomize order log n space reachability? And the answer took a while and took an interesting detour. So people asked this question right away, but people weren't able to come up with any really good ways to answer the question. So they asked a kind of a different question. They introduced this idea of universal traversal sequences, which is pretty cute. Okay. So to keep this simple, let's imagine that we have a deregular graph G. Okay. You can generalize this to non-regular graphs just by adding loops that make the degrees uniform. But let's just assume that it's a deregular graph G. Then what you can do is use the integers from 1 to d to label the edges leaving each vertex. Okay. And this labeling might not be consistent, right? There's two directions of an edge. They may get different labels. So it may be more accurate to say that I'm using the integers from 1 to d to label the exits from a vertex. Okay, and I do this for each vertex separately. Okay. If I do this, now any sequence of these integers from 1 to d defines a path or a walk through G. Okay. And it is called a traversal sequence from V if it covers or it reaches every vertex. Okay. And so you can think of a traversal sequence as sort of a really simple algorithm for visiting your entire graph. You just follow the numbers that are listed, specifying which edges you should traverse. Now, the interesting question is about universal traversal sequences. A universal traversal sequence, or a UTS, for a given n is a sequence of integers that traverses or covers every size n graph starting anywhere. So again, the simplest possible algorithm, conceptually at least, right? It's just a series of integers and a guarantee that if you follow the path, if you start anywhere in any graph and follow the path specified by these integers, you will cover the entire graph, visit all the vertices before you reach the end of the sequence of integers. No, so I'm sorry, this is for every size n deregular graph. Thank you. Okay. If the degrees change, you need to change the range of integers that you're using for your traversal. Okay. So this seems like kind of a cool idea, right? That all you would need to do is follow the sequence of integers and you could cover the entire graph. But the obvious question is, do these exist? Is it even possible to construct a universal traversal sequence? And it turns out the answer is yes. And the easiest ones will just concatenate all length n sequences of integers, okay, or length 2n or something like that, right? Because for any graph, you can look at some depth first search and that walks out a sequence of integers. And so if you happen to use that particular sequence of integers from that particular vertex, then you will end up traversing that depth first search and you will end up covering the graph, right? So from any starting point, there exists a sequence. And so if you combine all of the sequences, it seems kind of intuitive that you will eventually get to the one that works, right? Now, it's not quite this simple because, you know, if you use the wrong one first, it might take you to a different vertex. And once you're at a different vertex, you might need a different sequence in order to properly carry out a depth first search. But you can kind of go overboard, sort of mixing in all of the sequences a few more times. And sort of by pigeonholing, you can argue that at some point you will get to a place where you have the vertex and the right sequence at the right time from that vertex, and you will end up covering the graph. So there's some details to be worked out, but if you think about it, this basically requires a sequence of length about 2n factorial times n, because you have to consider all the different possible, you have to concatenate all the different possible sequences, right? Sorry, that's not right. Not 2n factorial. D to the n power times n, because there's that many sequences. Okay, so this is an incredibly long sequence. So the next question is, how short can we make our universal traversal sequence? Okay, and to highlight how challenging it is, there's a whole paper that gives a universal traversal sequence for cycles. Okay, so and this is a deterministic construction. So, sorry, go ahead.
How long is it?
And it is of polynomial length, which is what is exciting, right? I mean, obviously, a universal traversal sequence is going to have to be at least linear. So the natural question is, can you get one of polynomial length? Okay, and so for the cycle, somebody gave an explicit construction, and it's interesting to think, to realize that even on the cycle, it's hard, because the challenge is that it works for any labeling of the cycle, right? Each of those vertices has two leaving edges, and you have to decide which one is edge 1 and which one is edge 2. There's exponentially many possible labelings, and you've got this one polynomial length sequence that works for all of them. So that's pretty cool, but it does leave an awful lot of other graphs, like all of the trees, and then all of the higher degree graphs as well. Okay, but there's a beautiful result that uses the probabilistic method, which I've given very short shrift to in this class. I think I've mentioned it a few times, but basically, if you give a construction that works with probability greater than 0, okay? So you give a procedure for constructing an object that satisfies some properties, and you show that it works with probability greater than 0, and you use that to conclude that the object exists. So I am going to give you a procedure that has a non-zero probability of constructing a universal traversal sequence, and this will prove that universal traversal sequences exist. Does that make sense? Okay, and we've actually already done all of the work, right? So we showed that the expected cover time of our random walk is order n cubed. Right? And we concluded the probability that you take more than 2n cubed time to cover a particular graph, given a particular graph G and a starting point V, was less than or equal, was less than a half. Okay, and so if we repeat this k times, then the probability that we fail to cover is less than 1 over 2 to the k. Okay, but now let me ask, how many graphs are there of size n and degree d? Okay, and the answer, if we think about it, is to define a degree D graph of size n, basically we have to specify which are the roughly d times n edges that appear in this graph, right? Or another way to say it is we need to describe the d neighbors of every vertex, right? So basically for each of the n vertices, I need to specify d values between 1 and n that are the neighbors of that vertex, right? So basically, I pick the d neighbors of each vertex, and since I'm doing that for n vertices, it looks something like n choose d to the n. And this overcounts because really the endpoints have to agree with each other, but it's fine to be really sloppy here, right? And so this is about d to the n squared, or again, is upper bounded by d to the n squared. Actually, no, it's more like d to the n times d. Yes?
Is this
And
not n to the n times d?
let me think. Yes, thank you. It's n to the n times d. All right. We also have n possible starting points, but this is completely negligible. This puts in just another factor of d of n, so it's still n to the order nd, right? So this is the number of possible graphs and starting points. And if I do k random walks, of length n cubed fail to cover with probability 2 to the minus k. So the probability that I fail to cover from any start of any graph is at most 2 to the minus k times n to the nd by our good old union bound. Yes? So I just need to make 2 to the minus k times n to the order nd less than 1, which requires me to make k about equal to the log of this n to the order nd quantity, which is order of nd log n, right? So if I just do this many random walks of length n cubed, then the probability that I fail to cover any graph is less than 1. Okay, so I have a constant probability to cover all of my graphs. And the total length of this sequence is order n cubed times nd log n, which is equal to order n to the 5th times log n. So what I've just proven to you is that if I randomly generate a sequence of length roughly n to the 5th, it's probably a universal traversal sequence. And this proves that there exists a universal traversal sequence of length at most n to the 5th times log n. What do you think? Make sense? Any questions? So I will point out that this is the sine qua non of an existence proof. I've just shown you that the universal traversal sequence exists, and in fact, I've shown you that if you randomly generate a sequence, it's probably a universal traversal sequence. But I've told you nothing at all about how to construct a universal traversal sequence. We know nothing about its structure, its properties, just that most sequences are universal traversal sequences. It's a little wacky. Okay. So that's where things stood for, oh, that's interesting. Okay. They finally added a scratch erase gesture to this tool. I'll have to try it out later. So that's where things stood for a couple of decades. The universal traversal sequence result actually appeared in the paper which first analyzed the cover time of random walks on graphs. That was one of the motivations for doing it. But that still left open the question of deterministic reachability. And deterministic reachability, the de-randomization of our randomized algorithm was achieved in the 2000s. And it used pseudorandom number generation of the sort that we have discussed in this class. Okay, and it gave a deterministic log space algorithm for connectivity. And so this was a real triumph of complexity theory to finally, and you can't do better because again, you need log n space just to write down where you are. This kind of closed out that chapter. And again, the methodology, this deterministic algorithm really can't be understood as just a deterministic algorithm. It really is a de-randomization of the randomized algorithm that we already understand. So, and just another lovely example of how randomized algorithms can often lead to results in deterministic complexity as well. Okay. So that's the end of the story for reachability. I want to show you one more just remarkably beautiful use of a Markov chain in algorithms, but are there any questions about reachability before I go on? Okay, so we are going to come back to bipartite matching. Which I hope we all remember, right? We gave a PRAM algorithm for this, right? Based on matrix determinant. And putting random values into the matrix and computing its determinant, right? We showed how to first tell whether there is a perfect matching and then also how to actually construct one. And this was a big breakthrough in terms of its ability to solve things in parallel, but the runtime was not really great. And in fact, the best runtime for matching is about m times the square root of n. Okay. So I'm going to show you a really beautiful algorithm that beats this. But it also draws from this. This m root n time algorithm is based on augmenting paths from Maxflow. And again, we spent a little time talking about flow. This is something that I assume that you are familiar with, but the way that you turn a bipartite matching problem into a max flow problem is you take all of the edges of the bipartite graph, and now you direct them from left to right. And then you add a source on the left side and a sink on the right side. And you notice that there is a perfect matching, or sorry, let's generalize this. There is a matching of size k if and only if there exists an ST flow of value k, right? Because if you look at the flow has to go out on edges leaving S, right? One unit of flow can go through each vertex on the left. It then crosses to a vertex on the right and continues to T. So the edges that are used in the middle by the flow form a matching. Yes, and so you can compute matchings by computing flows, and you compute those flows by computing augmenting paths in this graph. There is a sort of when you look at what's happening with those augmenting paths, essentially what they are is they are paths that if you imagine that I currently have a matching that looks like this, and I'm interested in an augmentation to a matching that looks like, whoops, did that wrong. Yeah, so if I have the dashed matching and I want to augment it to the solid matching, right? That is, I'm augmenting from a flow of value 4 to a flow of value 3, right? Because I had the dashed matching, its residual edges actually point backwards, right? Sorry, let me draw this slightly differently in order to make it consistent with what I'm going to be doing next. So what I really want is something like this. So I have this matching, and I want to augment it to this diagonal matching. So what that means is that all of the horizontal edges, which are currently in the matching, give me backwards residual edges, whereas the edges that I want to put into the matching give me forwards residual edges, and that creates an augmenting path. And so what you see here is it creates a sort of alternation between edges that are in the matching and edges that are not in the matching that you swap in order to enlarge the matching by 1. Okay, so Goel, Koprolov, and Khanna in 2010 gave a super fast augmenting path algorithm for regular bipartite graphs, which is to say that all of the vertices have the same degree D. Okay. And quite surprisingly, it's based on a random walk. Okay. So let's suppose that you currently have 2K unmatched nodes, which say that you have K per side. Okay. And our goal is to find an augmenting path. Okay. Now, the current residual graph has, all edges going left to right, except for the matching edges, which are reversed and go right to left. So the very first thing that I'm going to do is I'm going to contract these n minus k matching edges. Okay, so I have a collection of unmatched vertices. I also have pairs of vertices that were matched, and I'm going to contract them. And let's imagine what effect this has on the augmenting path that we're hoping to find, right? So the augmenting path that we're hoping to find starts by traversing some edge from left to right. Yes? But the next thing it's going to have to do is traverse a back edge. And those back edges only exist on the matching vertices. So that's going to be a vertex that got contracted, right? And so you're going to go to one of these contracted vertices that isn't really on the left or the right anymore. Okay. Now, implicitly, you're now going to traverse the the back edge that is inside of this contracted vertex. And so that's going to take you back to a vertex that was on the left. And so now you're going to traverse a forward edge out of that vertex. And so again, that's going to take you to the right. And so now there's two possibilities. One possibility is that it takes you to an unmatched vertex on the right. And from there, you can continue on to the sink. Okay. The other possibility is that it will take you to another one of the contracted vertices where you will again traverse a back edge, right? And then again have this option of, well, either, now I'm on the left side after I traverse the back edge. And so again, I might go to a vertex that's already, I might go to a vertex on the right and escape, or I might go to another contracted vertex. But basically, I'm just going to traverse these contracted vertices until eventually I escape by getting to a vertex on the right and then making it out to the sink. So once I do these contractions, the augmenting paths that I want are very simple. They just go through a series of contracted vertices until they escape to a vertex on the right. Does that make sense? People still there? Everybody seems frozen. Yeah? Okay, so now an augmenting path goes from a left vertex into a sequence of contracted vertices into and this is an unmatched left vertex. And then we go through a series of contracted vertices and we come out on an unmatched right vertex. Okay. However, with the contractions, you know, the contracted vertices no longer form a bipartite graph. Who knows what kind of edges are there? And so it's still not clear how we can actually explore to quickly find that augmenting path. And this is where the Markov chain comes in. Okay, so as I mentioned, this augmenting path graph is a directed graph, and Markov chains on directed graphs are not nice. I made that point. So the insight of these authors was that they could make a nice undirected graph where you could look for a Markov chain. Notice that the contracted vertices have in degree equal out degree equal d minus 1. Okay. because they right, the left and right sides all had degree, the left side vertices have in degree 1 and out degree D. And the right side vertices have out degree 1 and in degree D. But that means that when I contract, I end up with in and out degree D minus 1. Okay. So now what I'm going to do is I'm going to add my source S with D parallel edges to each left-hand side vertex, each unmatched left-hand side vertex. And I'm going to add a T with D parallel edges from each right-hand side vertex. Okay. So basically, this changes things so that now every unmatched vertex has in degree equal out degree equal D. Okay. The left side vertices already had out degree D, and now I'm arranging them for them to also have in degree D by adding these parallel edges. And similarly, the right-hand side vertices had in degree D for the matching problem, but I've now added D outgoing edges so that they also have out degree D. So this creates a so-called Eulerian graph. Every vertex has in degree equal to out degree. Everybody with me on this? Okay. So again, just to make a concrete picture, so every unmatched vertex has degree D coming out or in, depending on the side, right? So now what I do is I make my S and my T, and I put D edges from every vertex on the left to S and from every vertex on the right to T. Okay. And now finally, notice that here, D has a total. There are n minus k unmatched vertices. And for each of them, I am adding D edges from a vertex. So the total degree of T is now D times n minus k. And that is also true of S. Okay. So now finally, I need to do this to finish the Eulerian construction. I add D times n minus k edges from T to S. Okay, because until now I've only had in degree to T. But now I've really made the whole graph Eulerian. And every vertex has the same in degree and out degree. Now, a nice fact is that the edge Markov chain on an Eulerian graph has a uniform stationary distribution. Okay. And this is the same proof as we did for the undirected case. The probability that I'm on an edge, the probability that I'm on an edge VW in the stationary distribution can be written as the sum over all of the edges that might precede me in the Markov chain of the probability that I am on that edge, right, times 1 over the degree of that vertex V that defines the step out of UV. Okay. And so if this is 1 over the number of edges, right, then we're sort of proving this is a fixed point, then what we get is d times 1 over m, d of v times 1 over m times 1 over d of v. And so indeed, if your probability of being on every edge is 1 over m before you make a transition, then your probability of being on every edge is 1 over m after you make a transition. And that proves that the uniform distribution is stationary. Okay. Now, why is this useful? Well, the fact that the uniform distribution is stationary tells us that the expected return time actually, let's see, how do I want to say this? So once we have the edge Markov chain, now we can go to the vertex Markov chain and conclude that it has a stationary distribution where the probability that you're on a vertex is just the probability that the edge distribution placed you on that vertex. And so that's just the number of edges that lead in to vertex V divided by the total number of edges, right? The probability that the vertex Markov chain is on a particular vertex is just the probability that the edge Markov chain is on the edge that ends up on that vertex. Yes? So now we have this nice simple description of the stationary distribution of the vertex Markov chain on Eulerian graphs. Okay, and so it's interesting. Eulerian graphs are directed, but they're only sort of locally directed. At a global scale, they're undirected, because if you look at any cut, the number of edges crossing from left to right is equal to the number of edges crossing from right to left. This follows from the sort of conservation of degree. And so in many ways, Eulerian graphs behave like undirected graphs and have these really nice Markov chains. Okay. Now, how do we take advantage of that here? Well, this tells us that the expected time to return to a particular vertex S, right, is equal to m divided by the degree of S, right? That's the fundamental theorem of Markov chains, is that your expected return time is 1 over your stationary probability. And yes, S is the source of this Markov chain. And if you remember, the degree of S was d times n minus k. Yes? And what is m in our problem? Well, m is equal to the number of edges that we started with, which is just the edges of the matching. Oh, sorry, the edges of the bipartite graph. And then we added in edges from S and edges to T. So that gives me another m plus 2, another 2d times n minus k. Yes? And so that tells me that this quantity is 2 plus n over n minus k. Okay, and remember that n minus k is the number of matched vertices. Okay. Everybody with me so far? Oh, I'm sorry. The degree of S is not n d times n minus k. K is the total number of, I only draw to matched, I only draw from S and T to unmatched vertices, of which I said there were K. So we get a K here, and we get a K here, and we get a K here. And so this turns into N over K. Good. Okay. But what is the formal definition of the expected time to return to S? It's the time that if you start at S, how long does it take you to get back to S on a random walk? Now, if I think about a random walk in this particular graph, what kind of path can take me from S back to S? Right? What does that path have to do in this Markov chain? Remember that all of the edges are directed from left to right. Yes, or stay in the middle, right? So how do I get back to S? Right. If literally all the edges were directed from left to right, I wouldn't be able to get back to S. So where are there edges that are directed from right to left that go back to S?
From T to S.
Exactly. You remember the last thing that I did to create this balanced degree was to add these D times, sorry, again, it's D times K, not D times N minus K, was to add these DK edges that return from T to S. And so in fact, the only way to return to S after you leave it is to go via T, okay? So what that tells me is that any path that returns to S goes through T. In other words, it's an augmenting path. Okay. And so what this means is that our random walk finds an augmenting path in expected time 2 plus N over K. Now, what is remarkable about that? Well, actually, let me make it even more remarkable. So our algorithm, right, to find a perfect matching, we need to run N augmenting paths as K, the number of unmatched vertices, shrinks from N to 1. So the expected runtime of all of these is just equal to the sum from K equals 1 to N of 2 plus N over K, which is equal to order of N log N, because we just have a little harmonic sequence there. So this tells me that I will find a perfect matching in order N log N time. Now, what's shocking about that? This is actually sublinear, right? The graph might have N squared edges, but you won't even look at most of them while you're finding the augmenting paths, right? You have to be a little bit careful about your, I mean, obviously you do this construction implicitly, right? You don't actually add all of these parallel edges. You just use weighted walks, right? And you're careful about how you do the updates. Like you can't actually afford to do the contraction of the left and right endpoints because doing so would be manipulating a lot of edges and changing pointers around. But you can manage that with sort of just by clever keeping track of what you needed to do, and end up doing just order n log n work, even if there are n squared edges in the graph. And so again, the key insight that was used here was that Eulerian graphs give you nice Markov chains that are as good as undirected graphs, and therefore the cover time of an Eulerian graph is very fast. And that's all that we needed. Any questions? Well, there are a bunch of open questions that remain, right? One that is still being worked on is, what about all those not regular graphs? Can you use some of these ideas, right? There's been some partial progress, but I think that a lot of this is still open. Like it would be really quite remarkable to be able to get a sublinear or even linear time perfect matching algorithm for bipartite graphs. There's also the question of de-randomizing this, right? I don't think that's been done successfully yet. I also think I feel like it can't be coincidence that we're using a Markov chain here, and we used the matrix representation, the Edmonds matrix, to do the parallel matching algorithm, because that matching matrix is basically the transition matrix of the Markov chain, right? So I feel like there's some deep connection between the parallel algorithm that we learned and this sequential Markov chain algorithm. But nobody's really figured out what's going on with that yet. All right, so that's the end of what I have time to tell you about using Markov chains for these combinatorial algorithms like connectivity and bipartite matching. Okay. The very last thing that I want to tell you about is about Markov chains for sampling. Okay. And in particular, what that means is sampling from complicated distributions. So let me give you two examples in order to motivate this. Let me give you one example in order to motivate this. In statistical physics, okay, you have this class of problems called Ising model problems. And Potts model problems, where you have a graph and you want to assign states, which we'll also call colors, to the vertices. And the electromagnetic interactions forbid you having the same state between two neighbors. Okay. Now, sorry, forbid is a strong term. More generally, they penalize it. And for those of you who've taken the right physics class, right, as the temperature goes up, the penalty for having the same state goes down. But at very low temperatures, then there's a very high penalty for having the same state. And at absolute 0, you're forbidden from having the same state as one of your neighbors. And physicists are very interested in the statistics of these configurations of states. And one of the things that they need to be able to do is generate a random configuration of the states. And so what this motivates is generating random legal graph colorings. Okay. So this is what I mean by a hard distribution, right? So it's easy for us to generate a random graph coloring. We just assign a random color to every vertex. However, if we want it to be legal, well, it's not even clear. I mean, deciding whether a legal coloring exists for a certain number of colors can be NP hard, right? On the other hand, if the number of colors is greater than the degree, we know a legal coloring exists because we can just generate one greedily. However, if we're supposed to generate a random coloring for the physicists, that's much harder, right? Again, we can generate a random coloring, but it almost certainly will not be legal. Okay. So all that we're trying to do here is sample from a particular distribution, but it's not clear how to do that. And so this is where we bring Markov chains to the rescue. So we use Markov chains. Okay. What we do is we design a Markov chain whose stationary distribution is the distribution we want. Okay. Then we start in some arbitrary state and we run the chain for a while until the distribution converges to the stationary distribution. And then we return the state we are in. And that becomes the sample from this very complicated distribution. Make sense? So all of the sort of depth is in this statement that we run for a while until the distribution converges to the stationary distribution. So I've shown you that there is a stationary distribution, but if you start in some other distribution, why should you believe that eventually your distribution is going to start to look like the stationary distribution? Well, the intuition here is kind of natural, right? The stationary distribution is the distribution that doesn't change. And we've already talked about how Markov chains are kind of forgetful, right? They only remember their most recent state and not their past. And so in a sense, any distribution aside from the stationary distribution encodes something about your history. And so for the Markov chain to truly forget its past, it needs to end up in the stationary distribution. Okay. But then there's the question of how long does this take? And this is where a lot of the mathematical work tends to show up in this approach, where you prove that within a relatively small number of steps, the distribution is going to be sufficiently close to the stationary distribution that you can ignore the difference and just take what you have as a sample from the stationary distribution. And notice that this allows us to sample from a complicated and And this works great if we are able to show what is called rapid mixing, which is that within a polynomial number of steps, we are near the stationary distribution. Okay, because then you have a polynomial time algorithm for sampling from the stationary distribution, for sampling from the distribution that you want. The other tricky part is this part, right? Designing a Markov chain with the right distribution. But there's some tricks that work pretty well for that. And it's often not hard once you understand the approach. So in the few minutes I have left today, I just want to fill in some of the details about what does it mean to be near the stationary distribution, and why might we hope to see rapid mixing. But are there any questions about the general approach that we're taking and why it's promising? No? Okay, so let's start to formalize some of this. Okay. So let's suppose we have our Markov chain and it has a stationary distribution pi, and we have some current distribution, which I'll call Q. We can describe the difference between these two probability distributions as using what's called the relative pointwise distance. RPD, which is just the maximum over all possible states of the difference in probability between the states divided by that probability in the stationary distribution. Okay, so relative to the probability that you're supposed to have in this state in the stationary distribution, how far away are you in your current distribution? Okay. And now suppose that the relative pointwise distance is some small delta. Okay. This implies that Q, the state distribution that you're in, is larger than 1 minus delta times your stationary distribution. Okay. Essentially, right, if the maximum difference here is at most delta, right, if qj minus pi j divided by pi j is less than delta, that implies that pi j is pi j minus delta times pi j is less than or equal to qj, and this will hold in all coordinates simultaneously. And what that tells us is that q is equal to 1 minus delta times pi plus delta times some other weird errors between the two distributions. Okay, so we can think of sampling from q as sampling from the stationary distribution pi with probability 1 minus delta and otherwise doing something weird. Right? And so we can think of doing something weird as sort of the error state of our algorithm. And so sampling from Q is basically a version of sampling from pi that works with probability 1 minus delta. So if we can force delta to be less than 1 over a polynomial, then we can say that sampling from Q works for sampling from pi with high probability. Right? And we are already comfortable with this notion of algorithms that work with high probability, and we know that we can, improve the probability, and we can take union bounds and all of that other good stuff. Okay, so if we can just get a probability distribution that is close to stationary, that's good enough for randomized algorithms. And now we can define the mixing time of a Markov chain to be equal to the number of steps needed from an arbitrary starting state to guarantee that the relative pointwise distance is small, e.g. 1 over a polynomial. Okay. And now, I mean, it's circular, but we can just say that given this definition of mixing time, we now have an algorithm for sampling, which is you run the Markov chain for the duration of the mixing time, and you report the state that you're in. Okay. Make sense? Okay, so I'm going to give a last lecture on Wednesday, where I'm going to give some examples of how you create Markov chains for interesting sampling problems, and then prove that the mixing time is small. Okay. We already talked about sampling graph colorings. And I'll do that by giving you a Markov chain for choosing a random coloring. Now, also, if you think back to when we did DNF counting, I talked to you about the relationship between sampling and counting, right? And so it turns out that if you can sample graph colorings, you can also count the number of legal graph colorings, which is, for physicists, basically about computing the partition function. Okay. I'm also going to sketch for you high dimensional integration, which is to say computing the volume of a convex body in high dimensions. Okay. And the way we're going to do this, just like with graph colorings, is by sampling a random point in the convex body. Okay. And again, we're going to do that by designing a good Markov chain that wanders around the convex body until you find a random point. So that will be Wednesday's subject matter, and that will conclude the course. Any questions? Okay, then I will see you on Wednesday.
Thanks.